In this video, we turn to force undamped mass spring systems. There are several interesting cases worth examining. To begin, recall the importance of the ratio between the natural frequency of the system and the frequency of the external driving force. One such case is known as interference. Suppose the frequency omega of the driving force is a multiple of the natural frequency omega 0 of the system. For our example, let the driving frequency omega be twice the natural frequency omega 0. So, if omega 0 is 1, omega will be 2. We take the external driving force F to have an amplitude of 1/2, and we assume the system to begin at rest, with both displacement u of 0 and velocity u prime of 0 equal to 0. If you pause here and work through the calculation, you'll find something interesting. If your computations are correct, you find that the displacement u of t turns out to be a linear combination of two cosine functions with different frequencies. 1/6 cosine of t is the solution to the homogeneous equation, whilst 1/6 cosine of 2t is the particular solution to the non-homogeneous equation. Let us decompose the different mechanisms at play to understand the behavior of the system. The input force f of t is a simple periodic function with constant amplitude equal to 1/2. But our interest lies in the system's response, u of t. That response is a linear combination of cosine of t and cosine of 2t, both with the same amplitude 1/6. When added together, these two oscillations interact. At times, they reinforce one another, and at other times, they interfere destructively. The result is a graph resembling a single sinusoidal wave whose amplitude varies in a regular pattern. At its maximum, the amplitude exceeds the value of either component alone. But what if the driving frequency is not exactly a multiple of the natural frequency? What if it is close but slightly smaller? This introduces us to the phenomenon of beats. Consider the following example. This time, let the driving frequency be equal to 0.8 times the natural frequency omega 0. So, if the natural frequency is 1, the driving frequency will be 0.8. For this example, we keep the forcing amplitude equal to 1/2 and the initial conditions u of 0 and u prime of 0 equal to 0. You can pause here and attempt to solve the initial value problem yourself. In this case, the solution for u of t is a linear combination of cosine of t and cosine of 0.8t. Here again, we're interested in the behavior of the system's response. The forcing function is still periodic, but it oscillates more rapidly since the driving frequency omega is less than 1. The system's displacement u of t is again the linear combination of the homogeneous solution and the particular solution, which are both oscillating functions, but with different frequencies. When combined, these two oscillations produce what we call beats. Here, the slowingly varying cosine acts as an envelope surrounding the faster oscillations. This phenomenon is particularly well known in acoustics, where two notes of slightly different frequencies interfere, producing a pulsing or throbbing sound. This concludes our discussion of forced undamped mass spring systems. Thank you for watching, and as always, remember to practice.